5 of our outdoor design series of classes, and I want to start off with a safety tip and talk about crane safety. If you're out at a substation and it's under construction, there happens to be a crane in the station at the time that you're there, you're now getting to see probably the most dangerous piece of large equipment that we deal with. And so if there's a crane active in the station, you always want to be aware of it. There should be a safety briefing, or whoever's in charge of safety at the site should be coordinating with you. And there's many ways cranes can have problems and end up hurting people. They can tip over. They also, if they have an inattentive operator, the boom, they can actually lose control of the boom and all. So you're safe. Your kind of rule of thumb of safety is that you're safe if you're more than a boom length away from the crane. Now, if you can, while you're at the station and the crane's operating, try to stay that distance away. It's in everyone's best interest. Now, it's not always that you can do that, but at the very least, there should be a safety observer watching the crane while you're doing your work, so that if the crane is bringing something towards you, someone is giving you a heads up and letting you know about that. Anyway, again, be safe around cranes. Are probably the most dangerous piece of heavy equipment that we encounter. Sam?
Yeah, as a young engineer, I know going out on site, I assumed that these crane operators knew what they were doing, they had good equipment, and for the most part, that's true. But as an engineer, I probably get out on site maybe 10, 15 times a year, something like that. And over the years, I've been within 20 feet of 2 significant crane failures. Where,
wow.
And these were big time, dropping 150 feet of boom on the ground and crashing through stuff. So don't think that these guys have it all under control and these are mechanically stable pieces of equipment, because there are instances where these things get away from them. And I mean, I've seen it twice, and I don't even get out and feel that much. So, yeah, definitely play heads up ball and don't assume that you're safe, because you're really not. Yeah,
and that little hard hat you're wearing, it's going to do very, very, very little for you if things truly go south on you. All right, today's topic is the structural aspects of station design. We've been talking up till now. Oh, excuse me, I forgot one thing. This is where we're going right now. The class we're doing right now is listed as number 1. Next week, and it may actually go into 2 classes, we're going to talk about grounding design, conduit design, conduits and raceway, and also lighting design. And then after that, I'm going to throw the consulting 101 at you, and then out in the distant future, design standards, talking about grounding calcs, IEEE 80, IEEE 605 for bus design, and there's a few others that I want to cover. But anyway, for today, here's today's outline, and we're going to talk about the structural aspects of substation design. Mainly going to be talking about steel and foundations. And foundations, the running joke is to call it cement. It is not cement, it is concrete. That'll be the first tip-off that someone would know that you really don't know what you're talking about if you call it cement. So let's delete the cement from our vocabulary. But before we get into this, I'm going to go through and talk about the basic sequence that we go through as we're designing a substation. I'm just assuming that it's going to be a greenfield substation, and I'll go through that sequence, kind of give you a frame of reference for the work you're doing now. And hopefully most of you have already seen this and won't be totally news to you. Anyway, the foundations that I want to cover, and there's always probably 1 or 2 others that I'll miss, but the main ones that we use in substations are piers, slabs, spread footers, and occasionally piles. I'm only going to briefly touch on piles. And then we'll talk about steel, the types of steel, some important aspects of connection points, and then talk about common structures. And I've got a couple of things to show you in Google Earth and some design drawings from an old project that I did. So anyway, it should be able to occupy a good class worth of stuff here. All right, this is the order in which we start projects. And in fact, taking a step even back from that, in my mind, there are really 3 parts of a substation design. There's the outdoor physical, which is covered in this slide. There's the indoor design, inside the control building, and the control and relaying and all the wiring that you've got to do. And then the third aspect of it is the procurement and specification of major equipment. And you got to have all three of these if you're going to build a substation. You'll look kind of funny if you leave one of them out. So this is the order in which we start drawings. The first thing that you've got to have at the beginning of a project is a one-line diagram and a general arrangement. And I would lump those together with even another document called design criteria, and I would call that the conceptual design. Someone has already got to have figured out conceptually what it is we need to build if we're going to build it. That kind of makes sense. And those are the documents that they will have produced to do that. If you don't have those documents, don't start running out and doing detailed design, because the stuff is inevitably going to change on you, and you're really going to be having a lot of rework if you do that. So anyway, we start out with our conceptual design, and the main documents that you want to see are the one-line diagram and a general arrangement. And I've got examples of these here that I'll show you in just a second. From those, you'll go and you'll do a general bus arrangement and some section views so that you can show where stuff needs to go. And then on your steel structures, you got to show what they've got to accomplish. What are you going to mount at what elevations, and how are you going to maintain your various electrical clearances? Now, once you've done that, then you can get your civil engineering friends to do for you a foundation plan. And a foundation plan is a really important drawing because that's the drawing that you're going to put your grounding and conduit design on, and perhaps your lighting design, depending on how large the substation is. Now, once you've started all these drawings, you're going to be continuing to tweak them and modify them through the course of your design, because there's a lot of coordination between the various drawings that you're going to create. I think that's kind of intuitively, hopefully that's intuitively obvious. So once you've got then the foundation design, then the civil engineers can start designing the steel structures and the foundation details, because every foundation, you're going to put a little box or circle on a drawing. Well, it's got to correspond to something that tells the contractor exactly what to build there. Anyway, once that's off and running, then you can go and do your detailed electrical design, conduit, grounding, lighting, plans and sections, and bills of material. And I've got an example of this. This is a project that I did. Actually, I can show it to you. This is a project I did called Alpine, and for geographic location, this is the Mojave Desert, Southern California, and it's there. It doesn't look like a lot, but it accomplishes a great amount, because this PV array it's connected to is 66 megawatts. So any day it's sunny, you've got 66 megawatts flowing through to the grid from my humble little substation. And as you zoom in on it, that's what it ended up looking like. Well, before it existed, these drawings did. And let me zoom this out a bit. Oops. Don't know how to get rid of that. No, I'm not doing very well. Yeah, that's what I'm trying to get rid of, is this. That's not it. Oh, well, at any rate, there's the substation. And this is the general layout drawing. I'm a little frustrated I can't get rid of that.
It's right at the bottom. It's closed tool. You can do that drop down again.
Oh. There you go. Thank you. Okay, so there's our substation. And this is one of the first drawings that we produced. And then from it, we went and did a bunch of section views. And so we've got the transformer here, some distribution circuit breakers, the feeders going out to the PV arrays are here, and then the cable that connects out to the high voltages over here. And now we didn't do bill of material callouts at that stage of the game, but we did have it dimensionally correct. And, whoops, there we go. So, and then from that drawing, the civil engineer on the project produced this drawing, which shows in fine detail where all the foundations go in the substation and a call out to them for the foundation details. Now here's a question for you. How accurate do these drawings have to be? Within what distance? I mean, we're not perfect. We can't make something absolutely accurate. Just can't do it. Do you know the dimensions that we worry about in a substation? We get everything to 1/8 of an inch. And if you have it within 1/8 of an inch, there's enough slack in the bolt holes that everything should be able to fit on the foundation, and everything should, be able to work out at that point. So anyway, this is in the development of the drawings. That's the next one. Now then, the civil engineer will put together of the foundation details. And notice that these are all, at least on this sheet, these are all pure foundations. And I'll be going into this here in a fair amount of depth soon. Okay, those are all piers, more piers. Now we have a couple slab foundations. And this one is for the transformer. And I'll give you some good examples of that. But then in the progression of the design, now I've got, notice that all those foundations are shown, and that's the drawing that I took and then put the grounding on. And lo and behold, a few grounding details. And then here is the conduit drawing. Again, I put it on the foundation plan. Does that make sense? And then once I've done that, I can go back to where we started from and fill in all the bills, the material bubbles on all of the section views, and then that produces my bill of materials. Does that make sense? That's kind of the progression of an outdoor substation design. Now then, at the same time, we're doing this, someone else, or maybe it's you doing this at the same time as a small project, are doing the indoor design. And this is the thing that's going to make think of it as the central nervous system of your substation. And you start out with exactly the same starting point, the conceptual design documents in the one line and the general arrangement. You're going to have to come up with an aux power, because we've got to have both AC and DC aux power to run things. Otherwise, it's just no fun if you don't have if you can't power up all your equipment. And then schematic design's the real big thing. You'll also, at about that point, do your relay panel elevations. And you need these things have to get done so that you can buy the relay panels and also buy the larger things in your control building, your battery charger, and that sort of thing. And then that all comes out in your control room layout and elevations. Once you have all of that and it's been reviewed, particularly the schematic design, you next do wiring diagrams and bill of materials. Okay, and that's the indoor design. Now then, the third aspect of this is the major equipment. And again, you start from the same exact documents, the same conceptual design, and you have to write specifications, send them out for pricing, figure out who's got the best deal. And it's not always price, although it usually is. And then once you've awarded it, you've got to keep track of their vendor drawings, because a lot of those vendor drawings you're going to need both for the indoor and the outdoor design. So you can see that all of these designs actually intertwine with each other. None of the three is really done independent of the others. And you need to have the situational awareness to understand where the other parts of the design are, so that you're sure that everything is moving together, and you don't run into a big problem, in the final QA check. Because for all these projects, ideally, we're going to sit down before it goes out and gets issued for construction, and have someone check the whole thing, make sure it's like a giant puzzle where all the pieces have to fit together. And design busts generally will happen if the people that are conducting the design don't talk to each other and aren't aware of what each other is doing. And if, for instance, someone has lost track of where the vendor drawings are for the circuit breaker, and they use the approval drawings in their design, as an example, not that I've ever done anything like that. Anyway, any questions on this? Does this ring a bell? Is this kind of what y'all see in your in the projects that you've been working on so far? All right, I'm seeing mostly head nods. That's a good sign. All right, there's our three-phase voltage waveform. I've got to throw that in every class. Make sure we're keeping track of why we're here. And now let's talk about foundations. Again, these are four types that I really want to touch on, and it's really three because I'm only going to kind of wave my hands a little bit about piling. It's kind of a very engineered type of foundation that fortunately we don't have to use too often. All right, this is my rendition of a pier foundation, and here are the key components of it. You have on the top something that we want to support. And in this case, I've just shown a bus support. Simple pedestal, insulator on the top. And the foundation underneath it is really pretty big. That's one of the first things that if you're not accustomed to foundations that will strike you is how large they are. You know, a foundation like that could have a couple of yards of concrete. How much does a yard of concrete weigh? Real simple one. Commit this to memory. A yard of concrete is 1 ton. It's 2,000 pounds is a yard of concrete.
Cubic yard.
And it's a cubic yard of concrete. It's a cubic yard, but no one calls it a cubic yard. They just call it a yard. And inside of this this foundation, in fact, the way we build this foundation, we take an auger, which looks like a big billdrit, or at least looks like big billdrit to me. And we put a big hole in the ground, and it can be a couple foot diameter. It could be 6, 8 feet diameter. You can make some astonishingly large pier foundations. But let's just assume this guy's 3 feet wide and call it 10 feet deep. So it's a little over a yard of concrete. And you usually have some reveal, so somewhere between 6 and 12 inches is sticking out above ground. Now, there's always going to be rebar in this. What would happen if we didn't put any rebar in the thing? Yeah, exactly. It would just crumble. It wouldn't last. It would crack and fracture. And if you're doing, say, pouring a little sidewalk or patio in your house and you don't put any rebar in it, well, how long is it going to last? It's going to make it a couple seasons. You start getting big cracks in it, and pretty soon you're going to be replacing it. So anyway, we put rebar in these. They're referred to as rebar cages. And so the process is you survey the yard very precisely, remember within 1/8 of an inch, and then you bring your auger in, you drill your hole, then you inspect the hole. Inspection is really important, and there's some criteria on this. Particularly, what you don't want down at the bottom is a bunch of uncompressed junk. That will always cause you problems, because think about how this is going to support the weight on it. And say you also had some overturn moment, and say maybe you were even trying to pull it up. Well, it's the weight of the foundation itself. It's the supporting of the soil at the bottom of it, and then it's the friction, the skin friction around the outside of it. All of those things contribute. So you want to inspect it to make sure that there's nothing that is compromising that. And there should be a qualified inspector on the job site. Now, inspection these days is not what it used to be. That Alpine project, we put one of the foundations of a very large pier, and the county, LA County's inspector wasn't there that day. And he literally was not going to let us energize this because he had not inspected one of the key foundations. Well, the inspector that we had hired said, oh, excuse me, I actually videoed the inside of that. And he had taken a video recorder and dropped it down that hole and had videoed all the way down the surface, going all the way down and to the base of it. Now that's an inspector. And that's the kind of thing that you have to have in these things. And it's not a game. These are really important aspects of this. So anyway, going back, then this is what you'll end up with. You'll lower the cage down into the hole and get it in precisely the right location, and get the anchor bolts, and very important, you get the anchor bolts precisely located, and then you fill it up with concrete. And you're going to finish the top of it so it looks nice and professional and brand new. And then there's some other aspects that go into this at this point, making sure you don't have any voids in the concrete, because air doesn't have nearly the strength capabilities that concrete does. And then that's really how you've got it, how your pour goes. Now you're going to have to wait 3 or 4 or 5 weeks for that concrete to harden enough that you can then put something on it. Sam, any other highlights that you can think of that I've skimmed over?
Yeah, one thing is you guys might have heard about the soils reports or geotechnical reports, and that's kind of the starting point for determining what the diameter of the pier is and how deep it will be. To the unaided eye, soil, it may appear that soil is soil. What difference does it make? Isn't it all kind of about the same? The answer to that is no, it's not even close to being the same. So there's 2 ways to do this. One way is there's some default values that you can use out of the IBC. And if you do that, and a lot of times clients, they don't want to pay the 5 to 10 grand for a soils report, and they'll say, okay, yeah, just use the default values. But the challenge with that is the diameter and the depth of these piers gets to be astronomical. And then once they see it on the drawings, they say, oh, well, how come these are so big? And you're saying, well, because we don't have a soils report. And then a lot of times they circle back and say, all right, I get it. Let's do a soils report. So it's usually money well spent.
I have a really good example of that. Out in the Dalles, we did a project, and some foundations that could have been relatively small because they were founded right on basalt were huge. And they said, why did you design them so big? And we said, well, why didn't you give us a soils report so we knew that this was down here?
Yeah, and it's a real problem, and nobody wants to pay the geotech
well,
to do it.
Another point on that that can really hit you, and you should really be aware of it. Usually in a soils report, there's a recommendation for the type and general size of foundations. If you do not agree with that, right then and there is where you need to raise it with the engineer that made those recommendations. Coming back after the project is done and telling him that you didn't follow his recommendations can often backfire on you, because in some states like California, part of the commissioning process is getting that engineer to sign a letter stating that you followed their recommendations. And it's a really unfortunate argument to have after the fact. Before you've gone down that road is the time to address that. So anyway. All right, any questions on pier foundations? Amalia?
Comment that has to do with, I don't know if we're going to talk about specifying type of concrete and curing times, because you just threw out some number of weeks that we
Oh yeah,
cure. And if you're not going to touch on that, I had an experience where I was called from the field and asked, can I put my breaker on the new foundation, after 2 days after pouring the concrete.
Oh yeah.
This gets to the specification we as Power put on our designs about the strength of the concrete and how the strength of the concrete gets determined once you poured a foundation. How do you know how strong it is after a certain amount of time? And really, truly for us, electrical types, not civil structural engineers, we really should come back to these guys and say, you deal with that, you tell them what to do. But in this particular instance, I got a little bit of an education about what they do.
Mhm.
And they pour these columns, and then we specify, let's say, 2,000 pounds PSI concrete or 3,000 pounds.
At a certain time duration, yeah.
And at a certain time duration, exactly. The two of them are linked, and then what happens is some columns get poured at the same time as the foundation gets poured, and then they get broken up with a certain amount of force at certain intervals of time, and you get a gauge of how fast concrete is curing, because in different weather conditions it cures faster or slower. So anyway, there's as much to our electrical stuff as there is to civil stuff, or vice versa. So when somebody calls and they're in construction, and the construction coordinator calls and says, "Hey, can I do this?" You say, "Wait a minute, I need to ask the people."
Yeah, you as the electrical or the electrical designer, you do not want to be taking responsibility for matters on the foundations. Those are really serious questions, and that's yes,
yay or nay.
yeah. Okay, now let me throw out a couple questions now to you. What do you do? Can you use pure foundations if you have groundwater? So that by the time you fill this up, it's full of water. You look down and maybe you've got a foot or two, and then it's water. You could stock it with fish. Can you now use a pure foundation? Civils can't answer this. How many say no? No. Incorrect. You can, and it's a thing called a trimmy. And what you do is you take a hose and you fill it up from the bottom with concrete, and it'll actually push it out. It'll push all the water out. It works like a charm. It is no problem there.
If they pull up too fast, you get voids in the concrete.
I'm assuming that you do it correctly. There is, bottom line, there is a technique, and the piece of equipment that it uses is a trimmy. There is a place in the Middle East, I think it's modern Lebanon, where there's evidence that someone used this technology like 4,000 or 5,000 years ago, which is to me is mind-boggling, but that's for a different time. Now here's another question for you. Can you use this if your soil conditions are such that it won't keep the hole open, and so it's going to slough in? Now can you do a pure foundation? How many say no? How many say yes? The yeses win again. And what you do is you put a casing down the hole to hold that open. And I've never watched this done. It's always been a puzzle to me, but apparently, yes, you can. Sam, when you put the casing down, does the casing it stays with the foundation, correct?
It can, or they can pull it out as they pull it up.
Oh, I see.
It's just the top 10 or 12 feet that are loose. After you get so far, the hole becomes more stable.
All right. Now, here's your third scenario. Say the soil has big cobbles in it, and so it's going to be hard for the auger to go through it. Now, can you do a pure foundation? No. That's the one rub. You got to be able to drill the hole. You got to be able to get an auger through it. We designed one. This is a Portland General project years and years ago, and they didn't give us a soils report, so we did what we had done on every other project. We had done the piers, and we went out there the first day they called us out to the field, and we're all hot and bothered and mad at us because we had designed a system that you simply could not work with. And we just said, well, you didn't give us a soils report, so, Anyway, when you have that, here's what you do. You do a spread footer. You don't have to go nearly as deep with this. And unfortunately, I don't have a drawing. I couldn't find one today of that shows this. But you may only have to go down 3 or 4 feet, and so you dig a big hole. You frame it up with wood, and then put your rebar cage in, and then you're going to pour the thing. I've never watched them do this. I've always assumed to get that neck part on the top is a second pour. But anyway, works like a charm. Takes a lot more manpower to do this. Piers generally are your cheapest foundation type. And generally, on pier foundations, contractors will figure out how much concrete you're doing, and they'll just bid it by weight of concrete. On this, if it's simple stuff, yeah, but a lot of stuff, it's a lot of complications can come up in the process. Now, there's a couple things I didn't really talk about in this that are also in the pier foundations, but notice I've got here these little pieces of steel. Anything that's blue in this diagram is steel that are sticking up, and those are your anchor bolts. Now, generally, most of our clients want leveling nuts, so you have a bolt holding it. The anchor bolt sticks up. You put a leveling nut at the base. The structure sits on that. Then you bolt down the top, and that way you can adjust the height and the plumbness of the structure that you put on that. Does that make sense? And that's your connection point. You never want to get anchor bolts out of place. The only thing worse than getting anchor bolts out of place is getting the whole foundation out of place. And the worst part of getting a foundation out of place is if you just barely get it out of place. If you miss it, say it's a 3-foot diameter pier, and you get it out of place by 5 feet or 10 feet, well, you can break the top off and pretend it never happened. But if you're off by 6 inches, oh my, that is just so depressing, because there are very few graceful ways to handle this problem. On a foundation kind of like this, but a lot larger, I had a project once where we got them out of place. And we had to drill in 2 6-foot long anchor bolts. And it actually worked, which was amazing. It was a really, really stressful thing. In fact, there are very few things that we do that can cause more stress than getting foundations out of place. Years ago, I had a project, or it was a series of projects, and we didn't have enough time to do it, and the coordinations were just going poorly. And I got a call at the end of the day, and it's November, and this project's in California in the Mojave Desert, and it's a drought year. And my civil engineer calls me up, and I can tell almost instantly he's crying. It's kind of weird. He's an adult. He doesn't normally cry. And what happened is he realized that one of his foundations was off by 1 foot. It was about a 3-foot pier. And he called the job site to get him to stop. And he was pretty sure they'd already poured it. They had to postpone the pour because it rained that day in a drought year in the Mojave Desert. And he was so relieved, it was so stressful for him that he literally was crying on the phone. So anyway, we don't want to cry. One of the tips that you can do to get your foundation or your anchor bolts in the same or in the correct place is make all of your base plate patterns symmetrical, so that if they're off by 90 degrees, it still works. I do not want to ever see rectangular anchor bolt patterns when squares would do. Just don't ever do rectangles. Do squares. If you're off by 90 degrees, it's fine. That one where we had to drill the 6-foot things in, that was because we were off by 90 degrees. The foundation was in the right place. Anyway, any other comments on this? Any other thoughts? Amelia?
So what is one tip or something to take away from this idea of misplacing your foundations? Like what would be a key thing to always keep in mind so you don't misplace your foundations?
How about work sober? I'm kidding. Yeah, most people do. I myself do as well. Actually, one of the things I will tell you, if you have a limited budget or limited attention for your QA check, put your extra effort into foundations as opposed to wiring. I can fix wires in the field. I cannot gracefully fix a foundation that's out of place. Try to use as many standard structures so that your things. We got a foundation out of place out of that project in the Dalles simply because there's always learn from your mistakes, and this is the one I learned from there. That we were putting it for a circuit switcher, and we didn't realize that the manufacturer had changed. It's a two-legged device. They changed the dimensions of the legs by 1 foot. Now, fortunately, the foundation was large enough. We just were able to drill in new anchor bolts. It was, the anchor bolts were sticking up like this, and they needed to be over 6 inches. Well, we just cut them off, drilled in new ones, and it really wasn't all that big of a deal. But just those things, and just eternal vigilance. There's just know, in most endeavors, you know what the worst thing can be, and you really work to mitigate that risk. Well, this is the worst thing I can think of, short of misspecifying major equipment. It's one of the reasons we generally have more senior engineers specifying major equipment.
Yeah,
Sam.
and just to add a little bit to that, it's not a 15-minute fix when this stuff goes south. I mean, this is easily weeks, if not a month, depending on how big the foundation is. I mean, they're going to have to demo out the old foundation, put in something new, and it becomes really visible to the client, and there's a lot of backpedaling that typically happens. So this is like super critical, big-time stuff that's easily caught with a diligent check. So that's kind of the unfortunate part, is it's so easy to catch.
The yellow line QA check, I swear to you, the single most important tool that we have at our disposal is a yellow pencil. If you learn how to do a yellow line QA check and really take that process to heart, you will avoid 90% of these problems. It's amazing, and when you do have a problem, you want to. Well, somebody gave me some advice that I think is worth passing on once. If you have a problem like this and it happened on your project, stand up, take your whooping, let people get mad at you, get that behind you, so now you can focus on the fix and learning from it. You always want to learn from it. You never, ever want to repeat the same mistake twice.
The Encore jobs I work on, even if I'm not working on physical, I check foundations for breakers. Encore uses Mitsubishi breakers, rectangular oval patterns.
Oh, and they pour in the anchor bolts.
Sometimes they are, sometimes they are.
Yeah.
Either way, half the jobs have at least one breaker where the foundation bolt pattern is 90 degrees from the bus. And it's either sometimes it's our mistake, sometimes Uncle likes to design their own foundations. And they get it wrong with the foundation.
Well,
Half the time, half the project.
on breaker foundations, if you make the slab square and oversize it, and there's a good reason to do this, and then epoxy in the anchor bolts, you'll never have that problem. And the reason to have on circuit breakers to oversize the foundation is so you've got a good work surface if you're a maintenance person going out to have to work on that breaker. Try and do this, have basically the face of the control cabinet here and the edge of the concrete right here, so you have nothing to conveniently stand on. It will not help you. And by buying a little extra concrete is pretty inexpensive in that situation. Any other thoughts before we move on?
One last thing
Matt.
is that if you can't get away from symmetrical foundations, you can add orientation marks to kind of show this is how it sits in the yard. That's one other thing you can do. North
Yeah.
west direction. But actually put a physical mark on both the foundation and the plan view and the details so that they can line it up. Because there's oftentimes different contractors and the concrete guy doesn't know anything about what's going on if there's following prints. So give them something to follow.
Well, and that is actually a really good comment right there. Realize that your foundation contractor will not understand electricity and really doesn't know much about about substations. So don't assume that they're going to have the background knowledge to really be looking out for you on this. Okay, let's talk now about our friend the slab. Now, a slab foundation we typically use for, I'm going to say three things, and as soon as I say this, I'm sure I'll think of something else. They usually go into the control building. They usually are used for transformers and usually used for circuit breakers. Now, there can be exceptions to all of those, but it's typically, as the name would infer, it's just a big slab of reinforced concrete. Now, in this case, the green thing I've sat on this is meant to depict a transformer. Now, transformers, by their very nature, are really heavy. You know, there aren't too many things that have the density of a transformer because it's mostly steel and copper on the inside, and what it isn't steel, or iron and copper, we fill up with oil that's fairly heavy to begin with. So we're talking a really heavy thing, and you don't usually bolt that down, you weld it down. And so one of the things that you'll put in your foundation for a transformer is steel embeds. Now, the amount of concrete that can go into these, and I'm going to show you one that's just bloody gigantic. These things could be 4 feet, 4 feet thick, and the size of half a tennis court. In fact, I'll show you one right now that is precisely that. This is SCE's Colorado River Substation, and we designed it here. And this is a transformer bank. You've got 3 single-phase transformers and a spare, then room for another bank that will share that spare transformer. So the foundations have already been put in. And it's actually kind of interesting because we can zoom in a little bit on it. And if I can convince it to quit doing that. Now, all these little things here, those are steel embeds. And that's plate steel. It's probably 3 or 4 inches thick and is tied into the rebar, so it is not going to move. And the idea is, during an earthquake, that and the transformer will act as a single body. And you won't get any differential, you won't get any movement out of the transformer. I mean, things are going to move, but you're not going to have the transformer sliding off of your foundation. Now then, interesting thing, this happened in the 70s. They have a substation out near Palm Springs that sits right on top of the San Andreas Fault, and there was about a 7.5 magnitude earthquake that hit this thing, and someone took pictures of it, and they kept it around the office for about a couple decades, and I got to look at it. And do you know, those welds, we're talking 2-inch thick, those welds ripped like paper. That's how much energy and motion you can get in an earthquake. Now, there's no perfect solution, is really what I guess I'm pointing out, but it's still interesting to see the sheer size of these. If we measure this thing is about a little over 30 feet wide. I think it's 38 feet long, 37 feet long, and it's about 4 feet thick. I can't do in my head how many yards of concrete that is, but that is a lot of concrete. That is a lot of mass. And, but then again, one of these transformers weighs probably around 1.2 million pounds. So it's, the two of them are about the same, probably in the same order of magnitude in weight. Anyway, kind of interesting. Any additional thoughts on this before we move on? All right, the last foundation I want to talk about, and I'm only going to kind of wave my hands about this, is a pile foundation. And in certain situations, the soil is so bad that you really can't do one of these. And a good example of that is down by the Columbia River. Anyone working on that I think we did a project at Blue Lake Substation. Maybe we didn't. Well, anyway, there's a substation down there owned by Portland General that's called Blue Lake. And we had to use pile foundations on it. The soil conditions, you go out and you look at it and you thought, well, yeah, this looks like normal dirt. Well, you go down about 2-3 feet of sandy dirt, and then you had what they called flowing sand. It was essentially water and sand mixed that had about the consistency of a milkshake. And then that went down 30 feet, and then you hit basalt. And so for that, under every foundation out there, there's multiple piers, piles that go all the way down. But on the surface, it looks normal because what you do, you've got these piles sticking out of the ground, and you pour what's called a pile cap on it. That's how you connect those piles that may be steel, they could be concrete, they could be wood. Wood doesn't deteriorate under those, where there's no oxygen there. There's all sorts of things over time that people have used for this purpose. But anyway, you then pour a cap on top of it, connect your anchor bolts in, and it really doesn't look any different from anything else. Now, during an earthquake, it's going to be really an odd thing to watch because ideally those foundations on the piles will not move while everything else liquefies, and it's kind of hard to imagine what it's going to end up looking like. Any comments on that? There's a lot of different systems these days out there for pile design. One thing, when I was a kid, they used to put pilings in for big stuff in the neighborhood I grew up in, and you'd hear the pile drivers. Well, now they found out that if you vibrate the things a little bit, they go in just like you're pushing a thumbtack in. And so you don't see big pile drivers out anymore. And then there's other ones that you can screw in. There's all sorts of different things. But again, if you need to have this done on your on your project, you as electrical designers, you're just going to see the pile cap. All the magic is going to be done by civil structural engineers. That's really a pretty big deal. Okay, Matt.
One quick thing on that is if you are in an old station and they have electromechanical relays, the civil guy may not be considering that driving piles may impact those electromechanical relays. So,
Awfully good point. Awfully good point. Yes, driving piles is actually, I don't know, violent is the right word, but it's what comes to mind. All right, let's change topics now and talk about steel. To me, steel is one of those, in fact, these two substances, concrete and steel, are just amazing, the strength that they have. Now, steel is strong both in tension and compression, where concrete is only strong in compression. But steel is just, it's magical how strong it truly is compared to just about everything else that we encounter day to day. I don't have any good gee whiz analogies. I'm kind of at a loss for metaphors on this. But compared, I think I've mentioned this before. One of our conductors is aluminum with steel reinforcement. When you're calculating the strength of that, you just ignore the aluminum. It's so small compared to those little, the tiny few strands of steel. Really an amazing thing. We typically are going to use three types or encounter three types of steel in a substation: wide flange, tubes, and lattice. Now I'm not going to address lattice because it really isn't used that commonly in substations anymore. And the way lattice is used, you can make towers and structures out of lattice that weigh a lot less, but they take a lot more manpower. So if you happen to be in an era where the price of steel is very high and the price of labor is very low, then lattice will work out. We are not in that era right now. And so we, compared to the price of steel, manpower is pretty expensive. So we don't want to have a lot of assembly out at job sites. Wide flange is an interesting thing. I don't have a slide of this, so let me draw something on the board. It takes advantage of an interesting characteristic that if you do something like this, and that's a cross-section view of it, and make a beam out of it, in this way, it's very strong. it's almost as strong as if there were steel actually here, but you save a lot of weight. Okay, now if you deflect it this way, it's going to deflect a lot more, and the designer of your structures has to take this into account for it. In tubes, there's two basic types of tubes that I have seen a lot around. One is simple a round tube. The other one is square tubes. And, you know, which shape is better is probably a lot. It has to do with what you're used to. And if you have some designs on the shelf that you've done before, you're going to want to stick with those. You could probably come up with all sorts of different arguments to justify your position as you're going through it. And I've got a few examples of these. Sam, you want to pontificate any more on the shape of steel for structures?
Yeah, the closed sections, the tubes and pipes are super stable, so you can have really long spans. The challenge with those, they're a little bit more expensive, and the grade steel is a little bit higher, so you're going to pay a premium. But you just want to meet your design criteria, so there's no need to call out the high-end, super expensive steel. It's not super expensive, but it's more expensive if you don't need to. So it's potential that a wide flange could meet your needs. So it's just kind of a balancing act. And one of the challenges with tubes is, if you weld on the outside, on the inside, you're going to mess up the galvanizing, and there's going to be no way to touch it up. Versus a wide flange, if you weld on one side, typically you have access on the back side to clean it up if you need to.
Well, and hopefully you're not having to do field welding. However, you won't go through your career very long before you run into a situation where you got to weld something. It just happens, whether it's a mistake or you're in an old substation and no one had envisioned making a certain connection at a certain point on a structure, and so you got to put a vang up there. Just the way life is. Galvanizing, Sam talked about galvanizing, and it's a really important thing. Steel corrodes. It'll corrode pretty badly when left out in the environment, but putting zinc oxide on it, coating it in zinc oxide is a way to pretty close to eliminate that. I don't know if it would be 100%, but pretty close to. If you put a good thick coating of galvanizing, which again is zinc oxide, you're going to have very little corrosion on your structures. Steel is generally purchased by weight, and the purchase price is based on what's called the black weight, which is before galvanizing. Now, there are a few places around that will galvanize structures for you, and their galvanizing pools are not infinitely large. And you have to design your structures so they can be galvanized in whatever pool you're going to be, your steel vendor is going to be providing. And most people that do this for a living, you get used to going to just one or two vendors, and you know what they have to offer. So if the pool is 40 feet long, don't design a 50-foot long member. Or if you have to, you know that you're not going to use that pool to galvanize it. Does that make sense? All right. What information do you, as the electrical designer, have to tell your civil structural brethren so they can design your structure for you? Well, first thing, you want to give them a plan and elevation so they can see the general shape of the whatever it is that they've got to build. And you also need to give them a loading tree. You've got to tell them what you're going to put up, mount on that structure. A good example being disconnect switches. Disconnect switches come in all different sizes and shapes, but they all are heavy. And you've got to account for that. It's one of the main things you want to account for in the steel design. Now, the drawings that we generally produce are what I generally refer to as erection drawings. They're not fabrication drawings. A fabrication drawing is going to have another layer of detail on it that is going to describe things such as the type of welds to use, and I don't actually even know what other information goes on them. But realize that there's going to be, when you send it out to a steel fabricator, they're going to do one layer of additional design on those. And you do want to have those drawings. Most people, at least, want those drawings incorporated into the documentation for the substation. That makes sense? All right. So here are a couple things to consider in your steel design. One is where are you going to, like on a dead end structure, where are you going to connect the conductors? That's one of the, I mean, that's why we call it a dead end structure, is you're going to have conductors under some sort of tension connecting to them, and the thing that you put on them is called a vang. And oddly enough, I don't know that it's a word in the English language. Every spell checker that I've ever had has tried to change it to fang, which doesn't convey any information properly. It's also, the vangs are often where change of ownership occurs. If you're building a substation and someone else, and it's your responsibility, the substation is yours, and someone else is designing the T-line, you got to have a demarcation point and tell them, okay, at this point, that way, you guys got to provide all the parts and pieces. From here on down, we will. And the vangs are generally where it's done. It certainly is the most convenient place to do so. That makes sense? Okay, I've already gone on a little bit of a rant about base plate design. That's another place that you're going to connect things. The other place that you're going to connect things, or the mechanism you're going to use to connect them, are simply bolt holes. And, this is another little thing that you can get wrong. We did a project out in, out by Hag Lake. And I'll never forget it. They went to the lowest bid. They went to a new steel supplier that was the lowest bid job. And where every bolt hole was supposed to be, 3/4 of an inch, they made them about a little more than 1/8 of an inch small. They had to bore out every one of those in the field. It was awful. It was awful. It was about a 2 to 3 week delay to the project. So again, something to keep in mind. Well, let's talk now about the types of structures we have in a substation. And hopefully most of you have seen some good examples of this. And I've got a Google Earth thing to share with you on that. One of the main ones is a dead-end structure. These are generally the largest ones, and you may have them to terminate lines, or if you've got a big transformer bank, you'll put dead-end structures either over the transformers or just in front or behind them, because you're going to connect it with strain bus to the switch rack. Now, depending on how much tension is on those conductors that have to land on your dead end will determine if you have to use an A-frame or an H-frame. Now, an H-frame has 2 legs. An A-frame has 4 legs. I think it's probably intuitive to most people that an A-frame will handle more tension than an H-frame. Does that make sense? I don't think I'm really rocking anyone's world with that observation. You will get more strength out of your A-frame by having the legs wider. But you're going to take up some useful space in your substation by doing so. So again, like all things, you've got to find a reasonable balance in this. The tallest A-frame that I have ever seen is 108 feet tall, and the connection point's about 104 feet up. That is a really big structure, and it has correspondingly large foundations for each of the legs. Okay? If you can come up with a design that you do not need such tall structures, you'll save a bunch of money. Okay? And give me just a moment, and I'll show you this substation that has this. Other things, the real simple ones are pedestals. You know, we put insulators on top of them for bus supports. Potential devices, you know, CCVTs and VTs go on them. Switch mounting is also another one, you know, that requires steel structures, and a wide variety of those things. Again, depending on just your situation. Are you mounting them up on a structure that's accomplishing something else? Because, for instance, you can put disconnect switches on dead-end structures. I couldn't find a good example of a box structure, but that's yet another way to mount disconnect switches. Here's a picture that I've used before, and if you look at this switch stand, it's 500 kV, it's a single-phase switch stand, and you'll notice you're using, that's almost entirely made out of tubular steel. Okay? Same substation, and, well, there's Mr. Wide Flange. Now, if, you know, this obviously is a wide flange. If you look at this structure right over here, which is a 65-foot tall bus structure, you've done wide flange legs, but your bridge across the top is tube. And if we had a better picture of it, you know, a better close-up of this, when you zoom in on the attachment to the vangs, there's actually a lot of science goes into just that attachment so that it actually is strong enough. So you're really getting the true strength of that member, that you know, the tension from the conductors is transferred properly to that member, and you don't just fail the thing as soon as you pull too hard at one point, because you can imagine the thing, you know, deflecting badly if you didn't design it correctly. And here actually is probably even a better picture of a similar structure. And again, the point you can see up here where the vangs are connected, a lot of design work goes into that little detail. In fact, there's a lot of aspects of this that are really interesting. Notice these members that go across these beams. As best I can tell, those are to prevent the thing from bowing out. Because notice that's not its strong direction. Its strong direction is back and forth, you know, going this way for that wide flange. Does that make sense? Really interesting stuff. You know, whether or not you're ever become adept at this, you know, enough that you actually could design it yourselves is really a separate issue. But just being able to look at it and see the features of it that you know ought to be there is really helpful. It really will serve you well as you progress. Okay, I want to do go back to my Colorado River substation and close off on a number of aspects of it. Okay, let's see if we can move that over. Can't. Okay, here's the substation. In fact, in a larger context, this is out by the Colorado River, which runs right down here, and the town of Blythe is right over here. So this is eastern Southern California. And the purpose of the substation is to collect solar in this area and bring that power back to Southern California. Okay, and as you zoom in on it, if it will zoom in, there we go. You'll see that the southern half is 500 kV and the northern half is 230. It always amazes me how much the 230 is dwarfed by the 500 kV. These are the main buses on the 500, and that's 65 feet tall. And it has to be 65 feet tall to have enough room underneath it to connect to disconnect switches. These dead ends going across here are the 108-foot ones, and they have to be that tall so that the line conductors can span over the main bus conductors. Does that make sense? Okay, so you end up with some awfully tall structures. Now then, here's a question for you. This bay is empty, but notice they installed the bridge for that structure. Why did they do that? Anyone offer a guess? This is an interesting point, actually. If they didn't install this, and you connect lines here, the line tension will deform the structure a little bit. Now, it may only deform it an inch or two or three, but once it's deformed, you will not be able to get that bridge in. There's no way on earth you're going to do it. It no longer will fit exactly. It'll be off by an inch or two or three. And that kind of blew my mind when I first found out about it. In fact, I first found out about this not from this particular situation, but there was an old substation. In fact, it's over on Johnson Creek. In fact, I think it's called Johnson Creek Substation. And it's an old box structure that was designed to fit into an oddly shaped piece of land for the substation. And it had this box structure, the legs, if you didn't need a bay, you didn't have to put the leg in. Well, we needed to add a bay to the structure, and so we just ordered another one of the legs, but it was going to go under a beam that was already spanning over that. None of us even thought about it, that beam was deflected about an inch and a half. So when they took our brand new, nice and galvanized member out there and put it underneath it, it didn't fit. And what we hadn't considered was that we couldn't just use one that was identical to what was out there, because we were putting it in a slightly different situation that none of us accounted for. And so what they had to do was take that thing back to the shop, take the top plate off, cut off about an inch and a half, put it back, put it in, and then it worked. It's an odd thing, but this is the same situation. If you're going to build a switch rack like this, and you ever want to use that bay, you got to build it, put it in then and there. If you don't do it then, it's not going in. Okay, there are ways that you could design this to avoid having to have such a tall structure, and Edison is looking at ways to try to reduce the cost of their substations. And there's a way I've got them. It's kind of complicated to show, but if you were to put the main buses right in the middle of the substation, use what's called a folded bus design, you could save a whole bunch of money in both steel and foundation costs on that. Anyway, for the rest of this, the steel that you see, kind of interesting. These structures are, my recollection is about 90, 95 feet tall. And again, you have to span over the main buses. And they put them just behind the transformers, so that your jumpers drop down to the primary bushings. But on the secondary bushings, you have bus supports that train the conductors out, and then you connect up to this side of that. This is the tertiary bus. A lot of transformers actually have 3 windings, and Edison uses the tertiary bus to connect line reactors to, or not line reactors, just tertiary reactors. So those are nice big slab foundations, but these are an interesting beast because they have a huge magnetic field associated with them. So you either don't use steel rebar, or you have to be very cautious in how you do it, because you can't have any closed loops. Anyway, last features of this is a jack bus, and this thing facilitates being able to take one of these transformers out of service and connect this spare in its place. Now then, let's look over on this side. This is a little 230 yard, and most of the time you don't think of 230 yards as being little, but in this case it is. And the thing I'd like to point out is just these circuit breakers. Now, the way Edison does their circuit breaker foundations, and it's hard to see in this, I understand, but they just put a big slab down, and then they will use epoxy anchor bolts to actually bolt the circuit breaker down to the foundation. It's a lot easier to do it that way. You never have problems in getting anchor bolts out of place. And it's also hard in a big slab when you've got a large pattern of anchor bolts to get all 4 of them in the correct location. So this is a method that I kind of like and would recommend. Now, one other aspect, and then I'll leave this and we'll wrap up. Some people like to embed conduits in foundations and have the conduit come up right in the right spot so it goes right into the control cabinet. And you'll probably see that in some of your designs. I recommend against that. It's just another thing to get screwed up on your project. You know, either whether we make the mistake or the people make the mistake out in the field. It's just a mistake waiting to happen.
One of the manufacturers on your big piece of equipment makes a mistake.
Just puts the ankle bolt or the control cabinet in a slightly different place. Absolutely. Yeah, they probably, it never even occurred to them that anyone really cared about that particular dimension on their outline drawing. Yep. Yeah, these things.
The control cabinet on the exact opposite side.
There's an afterthought.
You have conduit all the way over here.
Yeah.
You have to come out and route conduit all the way around.
Yeah. All right. Any questions about this? I think we can pretty well wrap up on this.
So Eric?
Yes.
This transformer bank, is that one transformer per phase?
Yes, that is one transformer per phase.
So how would a spare work in that case? You're just servicing one transformer and transferring the phase to the spare?
Yeah. Or say it fails and you have to put it over. Are you talking about how you make the jack bus work?
And yeah, and I've never heard that term before, so how do you make that work?
How about this? Rather than discussing that right now, right after we stop, I'm basically just about done. Come up and I'll show you. I'll do it. I got to draw something for you on it. All right. In conclusion, we started this class off with a discussion about the order in which we do the drawings or start the drawings when we're doing design work. And again, we talked both about just outdoor design in general, but also how the indoor design goes and how the procurement and specification of major equipment goes. We then talked about foundations, and we spent some time talking about 3 kinds in particular, the slab, pier, and spread footer. And then we concluded with a discussion of substation steel, and including kind of a brief introduction to typical steel types that we often use in our projects. And, you know, this is one of the classes that I could have gone on for another hour or so. And all I'm really trying to do in this is give you an introduction so that when you see it on projects, you go, oh, yeah, that's what he was talking about, you know. But anyway, with that, let's conclude. And we will be talking conduit, grounding, and lighting next week. All right, thank you. Yay.